All right, so I was asked to take a look at numbers 5 and 6, and then number 25. So we'll start with those, and then we'll take any other questions that you guys might have run into, okay? Numbers 5 and 6, I'll blow it up a little bit here. The issue with 5 and 6 was the fact that they gave us our angles in degrees and minutes. Now, if you looked back in your book or looked it up somewhere, you could have found out information about this. Whether you remembered or recognized what they were doing might have been another thing. But remember, degrees, minutes, and seconds. If I had, say, 50 degrees, 38 minutes, and 30 seconds, okay, the minutes and seconds you can think of just like you would time, even though we're talking about degrees, because there are 60 seconds in 1 minute, and there are 60 minutes in 1 degree, okay? So the way I would convert this so that I can actually do it in my calculator would be 30 seconds out of a minute is how much of a minute?
Half.
A half. So I would have then 38.5 minutes with 50 degrees. Okay? You just put the 30 over 60, 30 out of 60. Now there are 60 minutes in 1 degree. So I could figure this out. It would be 50 and 38.5 over 60 degrees. Okay, and obviously you could figure out what that is on your calculator. Alright, so that's how you would have to do the conversions. So if you think through this, 15 minutes is how much?
2.5.
Okay, it's 0.25. Alright, so 80.25 degrees. Okay? Now, if they give it to you this precise, don't round it before you do stuff. Okay? Leave it as 80.25. Here, 25 degrees, 30 minutes. That would be 25.5. Okay? Here we have 22 degrees, 45 minutes. 45 minutes is how much of a whole degree? 3/4, okay? So that would be 0.75. Okay? And then lastly, this one doesn't really come out evenly. You'd have to just do 88 and 35/60ths. So you could reduce that down to 7/12. 88 and 7/12 of a degree. Okay. And now you can actually, you have something that you can actually put into your calculator when you're finding your sines and all of that. Okay? Does that all make sense? Okay. I won't do the rest of those problems because now that you have them in degrees, I'm sure if you did the first 4 fine, these ones will be fine as well. Okay. All right. Then we had 25. Okay. Number 25. We have this flagpole. Now, one thing I will say. And those of you who are a little more artistic should like this. When you're given a problem where there's no picture given, you need to sketch something, alright? It doesn't need to be anything fancy. Just make a sketch that shows the information that you're trying to deal with. Yeah.
I got to this question and I couldn't, I tried to sketch it, but I didn't understand exactly how, so I didn't get to do it.
Okay. Well, let's go ahead and do part A, and then maybe we'll figure this part out. this one does have a few different elements that are a little bit strange. It keeps mentioning with the horizontal. Alright, so let's start out with our horizontal. By the way, using a straight edge when you're drawing your diagrams would be helpful. Okay, you can even use your ID and use it just to help you draw straight lines. Okay, but it says we have a flagpole that's at a right angle to the horizontal. Okay, so I'm going to draw my flagpole going straight up and down because it's at a right angle to the horizontal. However, this flagpole is on a slope. We'll make it green since it's, we'll assume it's grass. And this slope is going down at 14 degrees. Okay? So it makes a 14-degree angle with the horizontal. So this angle right here is 14 degrees. Oh, come on. Let me move it down a little. All right, everyone with me so far? Okay. All right. Here's our flag. All right.
You better draw a rectangle.
Or we can make it an Ohio flag. Those are cool. It's one of the few that isn't. It's one of the few that isn't rectangular. So it's like a blue circle there. And oh, whoops, that's red. So oh, there we go. There we go.
Nice.
Alright, anyways, not an artist. So now it says the flagpole casts a 16-meter shadow up the slope when the angle of elevation from the tip of the shadow to the sun is 20 degrees. Okay? So, let's draw that, okay? The shadow obviously is going to be on the ground, which is the green part, okay? So the sun is up here, it's shining down at an angle like that, okay? Now is this angle 20 degrees?
No.
No. An angle of elevation is always measured from the horizontal again. Okay? So, this is where this one's a little bit challenging. This is 20 degrees. Okay? And it says the shadow itself is 16 meters long. Well, the shadow is along the ground, so that's going to go from the base of the flagpole out to the tip of the, this would be where the shadow would end. Okay? So that's 16 meters. Alright? Yes?
Would the 20 degrees be like the top left angle if it's like also, yeah. No.
What do you mean? Like, if I drew a horizontal here, 20 degrees would be here, and 20 degrees would be here. If that's what you're talking about.
Sure.
Okay. Now, that actually is helpful, and this actually brings to mind something from geometry, okay? This is one of these properties from geometry. We have all these horizontals. Okay, let me get a nicer one drawn here. We have all these horizontals, and if all these lines are horizontal, what do we know about them?
They're
What?
180 degrees.
They make the right three angles?
Yeah, what?
They make the right angles?
No.
37.
No.
Complement.
If I have a whole bunch of horizontal lines, how do they relate to each other? They're
right
parallel, okay?
I was so close.
They're parallel. Now, that's why what Tristan just said is true. If this is 20 degrees, then so is this. Here are my parallel lines.
Whoa.
Here's my transversal. Remember that term?
Oh wow. That's going back.
These are what are known as alternate interior angles. Guys, this won't be the only time you see those in this chapter. Alternate interior angles, so this is 20 degrees as well. Okay?
Yay.
If you really want, this one out here is 20 degrees too, but that's not quite as useful in this case.
So that
Alright?
angle next to it is 70.
Okay, so yeah, the reason why we do that is because now we could pick up some other angles. We knew the flagpole is perpendicular to the horizontal, right? So this whole thing here is 90 degrees. So, yes, this part in here, inside this triangle, is 70 degrees.
So it's the one is the one on the bottom corner right next to the right angle 76
How'd you get that?
because it's a right angle and then you already have 14 so 90 minus 14 76.
Very good. Yeah, this would be 76. And also, here's another pair of alternate interior angles. Right here and right here. So this is 14 degrees, which means the whole angle is 34. Now we better double check to make sure these add up to how much?
180.
180, okay. And if you add them up, that's 110 plus 70 is 180, okay? So there's a little bit of geometry involved that we have to try to remember, okay? So there's our drawing. Use a variable to indicate the height of the flagpole. Alright, there we go. Now, this is kind of a mess. One thing that might be helpful would be to redraw this. Okay? We have that. We have that. And we have this. Okay? And let's fill in what we know. This was our height of the flagpole. This is the shadow that's 16 meters long. This is 34 degrees. This is 70 degrees. And this right here is 76 degrees. Okay? So now we have a triangle that we can solve. Okay? And a lot of times it might be helpful to redraw the triangle you're actually using so that you can see the relationships in order to use the law of sines. Okay? Are there any questions about how we got this diagram? Alright. Now we need an equation and then solve it to find the height. Alright? What equation could we write to help us find x? Brett?
16 over sine of 70 equals x over sine of 34.
Very good. 16 over sine of 70 equals x over the sine of 34. Okay? By the way, what do I know about x in this triangle? It's got to be smaller than 16 because it's across from a smaller angle. In fact, if we had found the other side would be the longest. And our flagpole is going to be the shortest side. Okay? Keep that in mind. Okay? And what did you end up getting? 9.52 meters is the height of our flagpole. Okay? So, kind of an interesting problem there. We've got a lot going on. But, kind of neat. Alright, so what do we want to measure a flagpole? Well, you may not want to measure a flagpole, but you might want to measure a mountain or something else. And you can use a similar concept. You know, measure some angles, measure a distance. You could actually use this, you know, now you'd have flat ground, so it'd be even easier. You could even use this kind of a thing by measuring its shadow to see how tall a skyscraper is or something. If you can see the end of its shadow and figure out how far away from the base of the building that is, then you could go out there, measure the angle it takes you to look up to the top of it, and do a little bit of trig, and you could figure out how tall the building is.
How do you find
You could use, what would they call it? Sailors used to use it to measure stars and figure out where they were on the. They would measure latitude and longitude by using the North Star, and they'd measure an angle. I can't remember what it is. Huh?
Astrolabe?
Might be it. Anyways, it's basically just something you hold up to your eye. You hold it horizontal, and then it has the degrees marked, and you look past it towards what you can see, and you can see what angle it is. You know, you just hold it up next to your eye. So. Alright, or surveyors have tools that they have it so it's perfectly level, and then they can measure.
We made the things you hold up to your eyes in geometry.
Did you?
Like out of whatever, paper and
Yeah.
straws and stuff like that. And
That's cool.
we measured it like somewhat angled and like lakeside and whatever.
Oh yeah.
And we calculated how tall lakeside was.
Cool. Yeah. I mean that's how they're able to measure, you know, things that are really immeasurable. I mean, I guess you could measure a skyscraper, but you know, how high is that plane flying? You know, how tall is that mountain? You can figure out different things, you know, and that's what surveyors do. You know, they obviously have a lot more sophisticated ways of doing it, but that's the basics of what a surveyor would do. All right. So, any other questions from other problems in the homework? 31? Okay, let's look at 31. The key to this one was remembering how the bearings worked, okay, in order to get your angles. We also had the alternate interior angles again, okay? I'm going to erase this and start over so you can see it kind of start to finish. Come on. All right, so let's walk through what we're given. Okay. We're given here that we've got these two fire towers. One's at Pine Knob and one is at Colt, and then there's this fire out here, okay? So these guys know that they are 30 kilometers apart, all right? But they don't know how far away the fire is, okay? So they do some measurements and can figure it out, right? The first thing here is the bearing from the Pine Knob station to the Colt station is north 65 degrees east. Remember how this is measured. You measure due north, and from that you measure a 65 degree angle towards the east. You know, so towards the right. Okay? So this angle right here is 65 degrees. Okay? Then it says the fire has a bearing of north 80 degrees east from Pine Knob. So again, we're measuring from the north, but we're measuring 80 degrees now towards the east. And then also from Colt Station, we have south 70 degrees east. as its bearing. So we're going to start at due south and measure to the right of that 70 degrees. So that angle right there is 70 degrees. That's not the angle in the triangle, that's just part of that top angle of the triangle. Okay? Does everyone understand what I've done so far?
Mm-hmm.
Okay. Now let's do a couple of other things to get some of the angles that are actually in this triangle. First of all, if we know this is 65 and this is 80, what angle is actually in the triangle? 15, good. Okay? So that's 15 degrees. And then right here, I diagrammed this over to the side. If this is 65 degrees, over here, from due south, you know, the north-south line is going to be parallel to this north-south line. So again, I have those alternate interior angles that we talked about earlier. So this right here is going to be 65 degrees. It's going to be the same measure as this angle. So now we know in this triangle, the angle is 135 degrees. Okay? Now you have angle side angle. You can solve that. You can solve that triangle now. Because the problem's asking, find the distance of the fire from each tower. So basically, they're wanting us to find, okay, they want us to find this distance and this distance, okay? So you set up your two equations, right, to find A and B. And notice, in order to set up our two equations, we do need to get this third angle. Okay? 135 plus 15 is 150, so this has to be 30 degrees. Now I have that pair across from each other, the 30 kilometers and the 30 degrees. So I can use my law of sines. Okay? And then you guys can take it from there. Alright? You solve it. The one is 42.43 kilometers away, the other is 15.5 kilometers away. Alright? Any other questions? Okay. Now, today what I want to look at,
Sorry,
yeah.
what did you say the answer for B was? Wait, not B. A. Oh, it's right there.
what we're going to look at today, just continuing our look at the law of sines, is another case. We've looked at when you're given two angles and a side between them. We've looked at the case where you're given two angles and a side that's not between them. Now I want to look at the case, it's known as the ambiguous case, where you're given two sides and an angle that's not between them. Okay? Now that leaves us with side, 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 and side, angle, side. Okay? How do we solve it if we know all three sides, we don't know any of the angles? Or how do we solve it if we know two sides and the angle between them? Those two cases will both be dealt with the law of cosines, which we'll look at next week. Alright? But we're going to look at this case for side, side, angle. Alright? I want to, your book gives you all of this, and I want to focus in on what I think are the three most significant ones. And those are the ones where you don't just get a unique triangle. Okay? Here, when A is acute, and we have A is less than the height of the triangle, okay? Or over here where A is obtuse, and the side across from it is shorter than the other side that we're given, both of those cases are actually impossible to make a triangle with. Okay? This one's a little more obvious because if this is an obtuse angle, then clearly it's going to be the largest angle in the triangle. So if A is shorter than B, you can't make a triangle out of that. Okay? You're going to have that A just kind of hanging and it'll never reach the bottom. Okay? Over here we have a similar case. It's not as obvious because you have an acute angle, but that third side doesn't ever quite make it down to close out the triangle. Now, it's possible to see this before you do all the work, but I give you an example here where this actually happens, and I just want you to see algebraically what ends up happening. Okay, so we have our situation here. We have an angle of 70, a side of 8, and this side is 3. Okay. Now 70 is still an acute angle, but if you look at this, solving for this angle x down here, using the law of sines, I would have sine of angle x over 8 equal to the sine of 70 degrees over 3. Okay? Notice I put the sines on top since I'm solving for an angle. Okay, it makes our algebra easier. So I take this and I multiply both sides by 8, and I get the sine of x equal to what?
44 times sine of 7. My bad.
Yeah.
Sine 70 over 3 times 8.
Yeah. So what does that come out to equal? Has anyone got that?
2.5.
2.5 something, yeah. So what's b? Or what's x? How is it undefined?
Because it's not between negative 1 and 1.
Yeah. Sine, remember sine always has to be between negative 1 and 1. So this is not possible, therefore there's no solution. It's impossible to make a triangle out of these pieces arranged that way. Okay? So, it doesn't take a whole lot to recognize it algebraically. You just have to pay attention. And if you don't even notice it here, if you try to do the inverse sine in your calculator, it's going to throw an error, and hopefully at that point you'll realize, there's something wrong. Okay? Now, I would go back, if you got an error on your calculator, I would go back just to make sure you set it up correctly, because it isn't like you're going to get a ton of these, but it is possible for that to happen. The other case I want to look at is right here, where this side A is between the lengths of the first side you were given and the height of the triangle. Alright? And I actually gave you one down here to illustrate. Okay? The nice thing about this is you really have to pay attention to this when you're using the law of sines. This will not be any kind of an issue when you're dealing with the law of cosines. There really isn't an ambiguous case for the law of cosines. Alright? But, as you look at this, if we're going to solve for A, we'd set it up, sine of A.
Wait, Mr. Hickson, what's wrong with that one?
Well, let's see. Okay? Let's see. It's not necessarily that there's something wrong, it's just unclear. Okay, and that's what hopefully we'll see here. So sine of A over 10 equals the sine of 85 over 9.98. So you see it's almost an isosceles triangle, right? So we know this angle is going to be a little bit bigger than 85 degrees. Okay? Now, as you guys solve this, you get sine of A equal to 10 times the sine of 85 divided by 9.98, and what do you get? .99, okay? .9981, I think it was 8 or something like that. Anyways. So now we need to do the inverse sine, correct? Alright. What do you get for A?
57.413.
87?
Oh, no, 57.413.
Something's not right there.
86.46.
86.46. So here's another rule. I told you I will always want you to give lengths in two decimal places. Angles will always round to 1. Okay? So we'll make that 86.5 degrees. Okay? So 86.5 degrees. And first of all, is that reasonable given our is that reasonable?
Yes.
Yeah, that answer makes sense, okay? The problem here is that's not the only possibility. Why is that not the only possibility?
Because.
We're dealing with
That's not
sine
the
here,
only
right?
answer? Is that what you mean?
Yeah, that's not the only answer.
Because sine has two times where it's positive. And the first and second quadrant.
Sine is positive in the first and second quadrants, yes.
So if you,
So 86.5 or think reference angle, okay? Here's 86.5
98
or
93.5.
93.5. Yeah, that's going to be our angle to there. 93.5. Okay? So that's our other possibility. You might say, well, that's obviously an acute angle. A little slow to computer's a little slow to respond. That's obviously an acute angle. As we drew it here, yes. Okay? However, we don't know how long this side is here between the two 80-some degree angles, do we?
No.
Okay? I drew it that long. However, what if angle A were here? Here's my 85 degree angle. That's 10 meters long, and that right there is 9.98 meters long. That's an obtuse triangle, right? That's 93.5 degrees, right? Yes.
how did you get the 92.5 again?
I used the reference angle because sine is positive in the first and second quadrants. So, because triangles can go up to 180 or go up to 180, I could have that first quadrant or I could have the second quadrant angle. Okay? We don't need to worry about this with tangent or cosine because you're either going to have a positive, which will give you first quadrant, or a negative, which will give you the obtuse angle. So, it'll be obvious. With sine here, though, we have two possibilities. And in each case, you know, this third angle would be a little different. This will be 1.5 degrees, or this one will be, what was it, 8.5 degrees. Okay? Both of those are valid answers. Okay? Now, sometimes you'll have a word problem that will define this as an acute triangle. Well, then you know this is the correct answer. Or maybe it was defined as an obtuse triangle, so you know this is the right angle.
Is
Okay.
that why on the homework 1 to 6 it said like 1 or 2 answers?
Yes, if there are two possible answers, you could have gotten two different ones. Okay. Yes, Jason.
How can I know there are two different answers?
Well, you'll know if, technically any of the ones that we've done, you could have considered the other angle where sine was positive. For example, let's go back here.
So we just did.
Okay. Well, we didn't solve any of these for angles. Oh, that's not you. Any of the other ones, there will be something obvious that makes it not make sense. Okay, so for example, let's say I had a triangle here where this was
82.
55 or something, and I was given, 6 and, let me do this, 6 and 5, okay, and I wanted to figure out this angle, okay, so I do the math here, and I get sine of angle A, I'm cutting some steps out of the way, but sine of angle A equals 5 times sine of 55 over 6. So what does that give me for A? Can someone do that real quick on their calculators? Okay, 0.682, so then take the inverse sine of that.
43.1.
43.1, okay. So, here's the thing. Technically, sine is positive first and second quadrant, so it's either 43.1 or it's 136.9. Okay? Now, this is not the longest side, is it? This is the shorter side. So I can automatically eliminate the obtuse angle. Alright? I know that's not possible. Because 5 is shorter than 6, so I know this won't be obtuse. So you can see cases like that and eliminate them quickly. Really, it most often happens when the two sides you're given are pretty close together. That can happen a lot when the two sides are close together in length and the other angle is either really big or really small. Those are kind of some things that'll tip you off there. Okay? Alright. The very last thing is the area. Okay? We have the area, and the fact of the matter is you guys already derived this yourselves. When I gave you the challenge problem yesterday, you guys dropped the height, and you used sine to help you find what the height was, didn't you? You saw that the sine of C equaled the height over A, so you could say that the height was then A times the sine of angle C. Okay? Now if you remember, I gave you the two sides and the angle between those two sides yesterday when I asked you to find the area of that triangle. That's why they call it the area of an oblique triangle. My name for it, this is not an official name, I just call it this, the side angle side area formula. Okay? Because if you know two sides and the angle between them, then you can find the area by using the 1/2 base times height formula and plugging in this height. Okay? So it's 1/2 times the base times the height. And then just out of habit, we usually put it in alphabetical order. Okay? 1/2 A times B times the sine of c. Since it's multiplication, we can reorder it. Alright? So there's our area. You guys derived that yourselves yesterday when you did the challenge problem. Okay? So, and that was impressive. A lot of you got that on your own. That was great. Okay? So you can find the area of any triangle where you know two sides and the angle between them, like this. Let's say I knew that, come on. Let's say I knew that this was 30 degrees, and I knew that this was 12, yes, I know it's not drawn to scale. Okay, and let's say that this is 15 meters here. If I want the area, I can take 1/2 times 12 times 15 times the sine of 30 degrees, okay, and just multiply that out. That's a half, so
90 times sine of
45.
45. And since it's area and we're in meters, it would be meters squared. 45 meters squared. Okay? Real simple formula that you derived yourself.